Welcome everybody to the sixth lecture of this course. I have just an announcement. Today's lecture is not live. I'm recording this lecture today, which is Wednesday, and I will have it broadcasted tomorrow because unfortunately for a personal issue, I cannot be with you today. So you can have questions, you can make me questions via mail or on MS Teams, but currently when you're watching this lesson, I won't be here in the classroom. So you can send me your questions later, but not right now because I cannot answer because I'm not here, of course. Anyhow, I think it will be still a good lecture, even if there is no interaction between us today. Before starting with the sixth lecture, I still want to talk about the Wisdom Bridge for a little while. Because, as you remember, I explained to you that the Wisdom Bridge is used when you want to measure a small change of resistance. We are interested in a small change of resistance over a large value of resistance which doesn't change and which, in fact, is not interesting for us. For instance, let's say that you have a strain gauge. It's a sensor of strain, mechanical strain. We will see how it works in the second part of the course. And let's say that it has a resistance of 120 ohms, something like that. And when you apply the force to the strain gauge, it will have a maximum variation of, let's say, 10 milliohms, okay? So the resistance of the sensor will go from 120 to 120.01 ohms, okay? You don't measure directly this resistance because it would be crazy to measure 120 ohms if you are interested in a variation of 10 milliohms. Therefore, as I told you, what you do is to use a Wisdom bridge. So you have a voltage source, you will have 120 ohms constant here, you will have another 120 ohms constant here, yet another 120 ohms constant here, and here you have your resistance that you want to measure, okay? And then I told you that you can easily calculate the output voltage. In this case, it will be if you remember, you can calculate it taking the voltages of the single potential here. Here you have A, here you have B. You can calculate VA and VB as two voltage dividers, and therefore the output voltage will be R plus delta R divided by 2R plus delta R minus 1/2 Vs, okay? This is VA, this coefficient times Vs gives you VA, this coefficient times this Vs gives you VB, and this is the difference. Now, let's plug the numbers. What happens when you have 120 ohms plus 0.01 ohms, okay? And here, 240 plus 0.01 ohms, okay? Of course, if delta R is 0, here you get 1/2, and the output voltage is 0. If delta R is different from 0, in this case 10 milliohms, which is the maximum voltage that we want to measure, the maximum resistance that we want to measure, what we'll obtain. If you plug the numbers, I just made my calculations before, you get something like this, okay? You get, oh, I didn't went very straight, so let's repair it. 0.00021 Vs, okay? So you have 0.00021 Vs. This coefficient, oh, sorry, mistake. I have to correct it. Sorry. See? It's minus 1/2 times Vs. Okay? So the first term will give you, let's make it all, 0.500. And now I have to watch back because I don't remember. 3 zeros. 2, and then 0.8 minus 0.5, which is 1/2, times Vs, okay? Which means, it is dropping down. Which means that we have 0.00021 almost Vs. Now let's say that, for instance, Vs is 10 volts, normal voltage that you can use for your bridge. And output, the maximum output voltage will be about 0.2 millivolts, okay? Fine. So the maximum voltage that you obtain out of your bridge when you have the maximum variation of delta R that you want to measure will be 0.2 millivolts, which is small. You can amplify this voltage. Why? Because the voltage the output voltage here will go from 0 to 0.2 millivolts, okay? For a delta R, which goes from 0 to 10 milliohms, okay? There's no idle value of resistance anymore, because idle value of the voltage anymore, because we removed this component, which doesn't change R, using a bridge. So the advantage of the bridge is that you can, in fact, remove the non-varying part of the resistance by putting the resistance that you want to measure inside a bridge where all the other resistances have the same value, okay? Now, the output voltage will be from 0 to 0.2 millivolts. Now we can amplify it. The question is how we amplify this voltage. We know we can amplify it without saturating the electronic, because there is not a large component of the voltage which doesn't change. We couldn't simply take a resistor here, inject a current, and then take the voltage here and amplify this voltage. We cannot, because we would have also a component of the voltage proportional to R, which is much larger than the component of the voltage proportional to delta R, and therefore we cannot amplify it. We would have a very large voltage proportional to R, which would saturate our electronic. So, how can we amplify now this voltage, now that we have only this small voltage output change? Well, somebody could say, fine, let's connect an inverting amplifier. We have studied how we can amplify a voltage, right? It was one of the lectures of 2 weeks ago. You have a small voltage, for instance, a voltage of a thermocouple, as we have studied, and as we have seen in the laboratory. I've shown you in the laboratory how you can amplify a voltage, a small voltage, given by a thermocouple. So why not using the same system to amplify the output voltage of a bridge, right? It's a small voltage. What's the difference between a small voltage generated by a thermocouple and the small voltage generated by a bridge? Fine, let's do it. So you have your bridge. Here we have our bridge. Here we have R plus delta R. And here is our output voltage. We need to amplify it. Fine. So what we can do is to use an inverting amplifier, right? And here you will have your output voltage. You put two resistances. We studied how to select these values of the resistances. And here we amplify, I don't know, by a factor of 1,000. Okay, so if the maximum resistance change, maximum change of resistance was 10 milliohms, this gave me a maximum change of voltage of, we said 0.2, roughly 0.2 millivolts. I use a gain of 1,000, and I get an output voltage which will be 0.2 volts, which is not very large, but still it's much better to measure 0.2 volts than 0.2 millivolts, right? No. Unfortunately, this system doesn't work. What's the problem here? The problem is that most likely this generator will be grounded, okay? Unless you use a floating voltage source, this generator in your circuit will be most likely grounded. And what's the problem? You probably remember that I stressed very much about the fact that the positive input of the operational amplifier must be grounded. If you don't connect the positive input of the operational amplifier to the ground, the amplifier itself doesn't work, okay? Now, look what you are doing here to the circuit. And let me find some, yes, I will use this color. Here, you have the ground. And the ground is connected to the point B of the bridge. And here you have the ground also, which is connected to the bottom of the bridge. So this resistance is connected at both terminals to the ground. It will have the ground here, and it will have the ground here. This means that this resistance is short-circuited, which is not good, because it means that this potential here will be necessarily at ground. So here I cannot get at point B half of the voltage Vs. You remember that the advantage of the bridge is that I subtract from VA half of the voltage of Vs. So I manage to remove the non-varying part of the resistance by subtracting the voltage proportional to that. And I do it having here a voltage VB, which is half of Vs. Now I don't have this voltage here anymore. I cannot make that trick where I add R plus delta R divided by 2R plus delta R minus 1 over 2 Vs. This minus 1 over 2, which corresponds to this voltage here, VB, is what made possible to have 0.50002 minus 0.5 Vs, which means that by having this negative 0.5 here, I get rid of this large part of the voltage. And I keep only this small varying part of the voltage. So I need this 0.5 Vs there. But if I connect this circuit here, then I force this point to be at ground. So effectively, it's like if here I force this to be 0. Okay? So it doesn't work anymore, this trick. So this is not a solution. I cannot use an inverting amplifier to amplify the output voltage of a bridge. The voltage between the point A and B cannot be connected to the input of an inverting amplifier. Somebody might say, okay, fine, let's use a non-inverting amplifier. But that's the very same thing. We must find an amplifier which doesn't have any of these 2 points, A and B, connected to ground. Okay? Neither the inverting nor the non-inverting amplifier is able to provide this condition. One point will be always grounded. So, this is the reason why when you have to amplify a small voltage and you don't want any of the 2 potentials to be connected to ground, for instance, like in this case, because you have to amplify a small voltage coming out of a bridge, you use a differential amplifier, okay? And now we will see how it works. Let me erase everything here. Differential amplifier. Fine. So differential amplifier. I will not draw again the bridge. You understand how it works. I will define VA and VB, and you know that VA and VB are the central points of the bridge, right? Fine. So differential amplifier is like this. Let's call this R2, R1, R1, R2. So here I will have VA. Oh, sorry. Let's call it VB. Just to keep the same terms. So VA. And again, VA and VB correspond to the VA and VB of the bridge, okay? So, okay, fine. Let me draw everything so it's obvious what we are talking about, okay? Here, your bridge. Here, yes. Here, you have the point A. Here you have the point B. Okay? So this will be VA. This will be VB. Okay? So here you will have the voltage VA and the voltage VB. Fine. How to solve this circuit? You can still use the superposition effect as we did for the non-ideal inverting amplifier or non-ideal non-inverting amplifier. Okay? When you have two sources, two or more sources of voltage and current in a circuit, and the circuit works in a linear range, what you can do is to shut down all the other sources but one and measure the output for that source. And then you do the same for all the other sources. At the end of the day, you sum up together the effects and you find the total output. So in this case, what we can do is to shut down VB and calculate the output for the VA. Then we shut down VA, we calculate the output for VB, and we sum out the effect. So, when you consider VA, you have to shut down VB, which is very simple, because then what you get, guess what? Is simply an inverting amplifier. An inverting amplifier which has two extra resistors. But as a matter of fact, it is still an inverting amplifier. So this is VB forced to be 0. So I ground the B input. If you ground the input, it means you force this voltage to be 0. Okay? So here you have R2, R1, R1, and R2. Okay? And here you have VA. So you shut down VB, you consider only VA, and the output will be, guess what? Negative R2 divided by R1 times VA. It's just an inverting amplifier if you think about that, because these two resistances do not have any effect. Okay? There is no current which can enter here. There is no current in this resistance. It's like if you don't have them or not. If you have, just make the parallel of them. Just consider that you have a single resistor here. If you have an ideal operation amplifier, that resistance is totally useless because it means that there is no resistance, there is no current flowing through that resistance, and therefore there is no voltage drop, and it doesn't change any potential in the circuit. We have already studied that. So this is the case for VA. You just have an inverting amplifier with some extra resistors here, which are useless. What happens for VB? Okay, we shut down VA. So I still have the same circuit. So I have R1, R2, R2. Now I shut down VA. VA now is 0. And I consider only VB, okay? Fine. Let's calculate the voltage output, okay? So, let's call this voltage here, let's find a color, because now it's getting complicated. So, the voltage here is, let's say, V prime. V prime is simply a voltage divider between R1 and R2, okay? So, it will be R2 divided by R2 plus R1 times Vs, okay? Now, since the voltage here is the same, the voltage potential here is the same here, so there is no voltage difference between the positive and the negative input of the operational amplifier, we can say that here we also have V prime. So we can calculate the current I as V prime divided by R1, okay? Again, this is the voltage V prime, but there is no voltage difference between this point and this point. So V prime is applied also to here. But if you take the finger here, you see that the voltage applied between this point, the ground, and this point, the negative input of the operational amplifier, will be the same voltage at the terminations of R1, okay? Just apply Kirchhoff's law if you don't believe me. So, the current, I, will be, therefore, V prime divided by R1. This current cannot enter in the negative input. It will flow through the resistance R2, causing a drop, which will be called V double prime. V double prime, let me do it better, will be therefore I times R2. I will be V prime divided R1, so it will be R2 divided by R1 times V prime, okay? Now, the output voltage will be V double prime plus the voltage here, which is 0. Okay, let's write it down. Here, the voltage is 0. So the output voltage will be V double prime plus 0 plus V prime. Okay? So, the output voltage will be V double prime plus V prime. Okay? So, V double prime is R2 divided by R1, V prime plus V prime, which means that we have R2 divided by R1 plus 1, V prime, and we continue here. So, the output will be R1, and you have R2 plus R1 times V prime. Now it's time to check what is the value of V prime and plug it here, okay? So we have R2 plus R1 divided by R1 times V prime, but V prime is R2 divided, guess what? R2 plus R1 times Vs, okay? Not Vs, sorry, Va. Oh, VB, sorry. So the volt, now I should go back and record all the explanation again, because I realized that this is a voltage divider between R2 and R1, and the input is VB, okay? Sorry. So where was I? Here. VB, okay? Fine. So, of course, you can erase this, and the output voltage will be what? R2 divided by R1 times VB, okay? So, when you consider the first case, A, you get this output, okay? When you consider this case, B, you apply only B and you shut down VA, you obtain this output. Now we have to sum the effects, okay? So let me erase this part where I show how I derived V output in the second case, when I consider only VB and not VA. So if you don't mind, take note of this, and I will erase it. Okay? The advantage of recording a lecture is that students can simply play the stop button, and then they can simply write down all the notes without rushing. So, the total output voltage will be R2 divided by R1 minus, R2 divided by R1 VB minus R2 divided by R1 VA, and again, I'm dropping down. So let me, just for sake of making a good lecture, R2 divided by R1 VB negative R2 divided by R1 VA, and of course, it's R2 divided by R1 VB minus VA. Okay? Now, you see that we achieved our results because we have an output which is larger, which is proportional to the difference between VA and VB, which is exactly what we wanted because we put our voltmeter here. Okay? When we put our voltmeter here, it means that we want the output voltage as the difference between VA and VB. So what we do is to obtain an output voltage at the end, at the output of our differential amplifier, which is exactly the difference between VA and VB multiplied, amplified, by a gain which is given by R2 divided by R1. For instance, you can decide to have, I don't know, 100 kilo ohms here, and 1 kilo ohms here, again 1 kilo here, and 100 kilo ohms here, and you get a gain of 100. So your output will be 100 times the difference VB minus VA, okay? That's exactly what we wanted. What's the advantage? The advantage is that now neither the point A nor the point B are connected to ground. As you see, they are very far from ground. There are some non-negligible resistances between the point B and the ground. You see? You have a 100 kilo ohms, which is a very large resistance. So you can, to some extent, consider them not connected to ground. Now, of course, there will be some current here, okay? If you want, you can calculate as an exercise the values of these two currents, okay? So it's not true that here I have no current leaving from these points, which, if you remember, was one of the conditions that we assumed when we calculated the output of this bridge. If you remember, I said, how do you calculate VA? VA is a voltage divider between this resistance and this resistance. And I told you, be careful. Here there is a point which is connected somewhere else. So you might think this is not a true voltage divider between this resistance and this resistance, because there is something else connected in the middle. But, so these resistances are not in series. But I told you, well, the current here absorbed by the voltmeter is almost zero, okay? The current which is absorbed by the voltmeter is almost zero. So you can assume that the voltmeter is not even there, right? If it absorbs ideally zero current, you can assume there is no voltmeter connected between point A and B. And this means that you can have these two resistances actually in series, because you can see them like this, okay? Because the voltmeter here doesn't exist. You can remove it. So these two resistances are in series. Fine? So if these two resistances are in series, you can use the formula for the voltage divider. This is not true anymore, because here there is some current which flows from the point A to the resistance R1 and from the point B to the resistance R1. There is a current, you can calculate it. So it's very small, right? So to some extent you can neglect it if the difference they introduce to your bridge is negligible, okay? But there is some current, and you don't like it. If you want to do something very precise, yes, okay, I want my voltmeter to be ideal, as much as ideal as possible, as close as ideal as possible, right? So you want this current to be as low as possible to imitate an ideal voltmeter. And this circuit is not nice, because, yeah, some current is still flowing to the differential amplifier. So what are we gonna do here? For sure it's better than the previous circuit with the inverting amplifier. In that case, it was terrible. I was connected this point to the ground. The bridge was not gonna work at all. In this case, it works fine. Still, I would like these currents to be totally zero, or very, very small. So, in this case, you had to add an extra component. I will erase everything so that I have space to draw the new circuit. The base of the circuit is still the differential amplifier. But before the differential amplifier, we add something else, okay? Maybe I shall ask my technicians to erase these parts when I clean the board, which are probably very boring for you. And also, it's a temptation, because you will go to WhatsApp, read your messages, and then you don't follow the lecture anymore, okay? So I will take note to ask to remove these parts. And if you hear what I'm saying, it means it didn't work out. Okay, fine. Again, this time I will not draw the bridge again. I only use VA and VB. And what am I gonna do here? So, use this circuit. Let me draw it better, because you deserve the best. Okay. So I will call it this RG. This will be R, I don't know, star. Be careful here to the positive and negative input, okay? Remember, the feedback must be always to the negative input. So here, I feed back from the output to the input. So this must be connected to the negative. And again, here, I feed back from the output to the input. So this should be the negative input, okay? So here I have VB, here I have VA, and let's see what is the delta output, the delta voltage that you get at the output of this. Now, you see that I'm not connecting anything to ground here. It's floating. I just want to see what is the difference between the voltage at this output of the operational amplifier and the voltage at this output of the other operational amplifier, okay? Fine. Now, as you remember, as I told you, you always have to apply the three magic rules of the operational amplifier. The voltage here between the positive and negative input of this operational amplifier is 0. The voltage input between the voltage between the input, positive and negative input of this operational amplifier is also 0. And therefore, if you watch at the Kirchhoff law between this network here, okay, if you consider this net, you have this voltage between these 2 points, which is VA, oops, the voltage between these 2 points is VA minus VB, okay? So I can draw it like this. Is VA minus VB, okay? Maybe it's better if I draw it with the white color. VA minus VB, okay? Then I have 0. Then let's call it VG. Then plus 0 plus negative VG, which is the voltage on this resistance, plus 0 equal 0, okay? So it means that VG, the voltage on this resistor, is equal to VA minus VB. This was very complicated way to show what was obvious. If I have these 2 points here, which go to the positive inputs of the operational amplifier, because there is no difference between the positive and negative input of the operational amplifier, I find this voltage between the positive inputs of the operational amplifier, but also between the negative inputs of the operational amplifiers. And these negative inputs are connected directly to RG, okay? So the same voltage that I have here, VA minus VB, will be at the terminations of RG, okay? Fine. Then the current, let's call it I, which flows in the resistance RG, will be clearly VA minus VB divided by RG, okay? I know the voltage between the terminations of RG, I divide it by RG, and I get I. This current cannot flow from the negative input of the operational amplifier. It must come from this resistance. And as well, it cannot go to the negative input of the operation amplifier, but it must flow through that resistance, okay? So the current, let me draw again the circuit to make it clear. So here I have VA minus VB. Here also I have VA minus VB, which generates a current I. And this current I flows this way. Okay? Because there is no current here and there is no current here. So, when you watch, this was R star. These three resistances have always have the very same current I. So the output voltage here, or the difference in the output voltage, will be given by the current I times R star, which gives you this voltage on this resistance. Then the current, the volt VA times VB, plus the voltage here on the voltage drop on this resistance, okay? So in total, you can have the, where is this? You have 2 R star plus RG. This resistance was called RG, fine. And I, we know that it is VA minus VB divided by RG times 2R star plus RG, okay? Fine. So if you want, you can write, you can take this here and you have 1 plus 2R star divided by RG times the difference of voltage that you want to amplify, which is VA minus VB, okay? Fine. So what you do is here, what you obtain is an output voltage difference between this point and this point, which is equal to the input difference of voltage, VA minus VB, times this coefficient, okay? Which is not the main purpose of this circuit. Sure, you amplify by this gain, by this coefficient here, the difference of voltage VA minus VB. But amplifying here is not the main purpose of this circuit, because at the output, you still have a difference of voltage, and neither this terminal nor this terminal is to the ground. So we didn't solve the problem of transforming a difference of voltage into a single-ended voltage which has one terminal connected to ground. So here, we will still need a differential amplifier, okay? Let me draw it. Here, at the at the output of this stage, we still need okay, R2, R1, R2, R1, and this is connected to the output. Finally, here, you will have a differential amplifier, the very same circuit we saw before, and the output voltage finally has one terminal connected to ground, and we are happy. Here, no. Here, you have a difference of voltage, VA minus VB, and no terminal can be connected to ground. And here, you still have the same situation. Here you have a difference of voltage, which is bigger than this. So here you amplify it, but still you are not referred to ground. So why do I need this circuit? Can't I simply select bigger resistances here in order to have a bigger gain there and get rid of this part? Why do you need this part at all? I mean, just to make the difference of voltage bigger by this coefficient? Well, also this circuit is making the difference of voltage bigger. So select proper values of R2 and R1, and you can get rid of this part, which is just amplifying the difference of voltage, right? It doesn't bring any voltage to ground, refer to ground. It's simply making the difference of voltage bigger, okay? Right? Not really. There's a huge advantage for using this circuit, right? You know what is that? Look at the input. I will draw better this circuit, or maybe we can watch it here. Look at the input here. Now you connect VB and VA directly to the positive input of an inverting amplifier, right? And do you remember one of the magic rules of the operational amplifiers? The current which enters the positive input is 0. Sure, I know they are the bias currents, but they are very tiny. At this stage, we can consider them basically 0. So, the difference between a differential amplifier without this input stage and the operation and the differential amplifier, which includes this stage, is that if you connect VA and VB at these 2 points, then there is a current. I told you, you can calculate it. Do it as an exercise. There is a current which enters, and this current affects our bridge. You don't have an ideal voltmeter because the circuit which amplifies your voltage absorbs a current. When you add this input stage before the differential amplifier, then you have no current which enters in the, no current which is absorbed by this stage, because you have your points VA and VB, which come from the bridge, connected directly to the positive input of the operation amplifier. And there is nothing else, you see? You have simply this connection and nothing else. If the positive input doesn't absorb any current, then from the bridge, there is no current which goes to the amplifier. That's exactly what we wanted. Okay? The same for this. Okay? So what you do here is to have your bridge connect VA and VB directly to this input stage, and no current will leave the point A and the point B, because these points now are connected only to the positive input of these two additional operation amplifiers. Okay? So if you really care about having zero current leaving the bridge, which is the ideal condition, then you use this circuit, which altogether, if you take this input stage plus a differential amplifier, is called instrumentation amplifier. Why instrumentation? Because this is typically used for reading output of measurement systems, instrumentation, where you cannot connect neither one point nor the other of the voltage to the ground, okay? So, this was a very important part that you will never have to forget once you want to use this kind of circuit, okay? Always be sure, before amplifying a voltage, that you can connect one of the two terminals to the ground without affecting the circuit. If you cannot use inverting or non-inverting amplifier, but you must use either a differential amplifier, or if you really want zero current leaving the circuit, you must connect an instrumentation amplifier. So you must have this input stage before the differential amplifier, fine? Now, this very long introduction, and I really apologize for that, but it's very important, okay, that there are many things that you can study, and this is one of the things that you should really remember, because for practical applications, this is very important, okay? Otherwise, you go there, you take an inverting amplifier, and you say, okay, but my teacher told me I can use this to amplify voltage, then everything will be screwed up, and you say, oh, my teacher said me something not really correct. And you will blame me for that, okay? Now, let's recap a little bit what we have done so far. We have studied how to measure voltage. For instance, if there's a small voltage, you amplify it with an inverting amplifier, non-inverting amplifier. We studied how to measure resistance. We studied how to measure a small resistance, so comparison method. We studied how to convert resistance into a voltage. Remember, you had the resistance to voltage converter. So maybe I should really use this. Otherwise, you cannot see anything. Ole. So I said, you can measure a resistance with comparison method. You can use, for instance, a resistance to voltage converter, okay? So this is the unknown sorry for the spelling, unknown resistance. You know the input voltage, you know this reference resistance, and the output will be proportional to the resistance, okay? You studied how to measure an impedance, okay? So if you want, you can measure an impedance. And we studied how to measure an impedance using a resistance here an inductor, and then you have to, remember, use a synchronous demodulator to find the real and imaginary part of the voltage. And we studied how to measure a current. If it's a regular current, you can use a current shunt, or for instance, if it's a very small current, you can use a current to voltage converter, okay? So in the laboratory, I made the example of having a photodiode. If you have not done the laboratory, do it now. So for instance, here you have 100 kilo ohms. Here you have a very tiny current produced by the photodiode. And what you do is to use this circuit where the current cannot enter in the negative input of the operation amplifier. Then it goes through the resistor, 100K, and you find here an output which will be proportional to the current produced by the photodiode, okay? This will be the current produced by the photodiode. It will cause a voltage drop on this resistance, and you will find at the output this voltage drop proportional to the photodiode. So finally, you will have a current of the photodiode multiplied times 100,000 times, okay? Fine. By the way, in the laboratory, I explained to you, or I gave you a task, a question, which is to explain why I use this circuit where I use an operation amplifier to get an output voltage which is given by, let's call this V prime, negative V prime, which means, which is negative I of the photodiode times 100,000 ohms, okay? So I simply multiply the current of the photodiode times this resistance. Why I cannot use, the same photodiode if you want, you can count it, who cares? With 100 kilo ohms like this, okay? The current of the photodiode will still flow through the 100 kilo ohms, and it will cause an output voltage, which is the current of the photodiode, times 100 kilo ohms, okay? So the formula is the same. The output voltage will still be the current of the photodiode times 100,000, okay? So why I cannot use this circuit and I must use this circuit? This was the, of course, they behave in a totally different way. So why I should use this circuit and not this one? That was the question of the laboratory. And so on, we studied how to measure voltage, resistance, a small change of resistance with a Wheatstone bridge. In all these cases, at the end, what we do is to obtain a voltage. Here we obtain a voltage, here we obtain a voltage, we measure an impedance, and we obtain a voltage. And finally, as you know, we must digitize this voltage. So basically what we do almost always is to take the physical quantity that we want to measure, either current, resistance, impedance, whatever, and to convert it to a voltage. Because when you have a voltage, then you can convert it into digital code using an analog to digital converter. If you remember, it was the ADC, analog to digital converter, was the topic of the first lesson, I guess, yes. We studied how to digitize properly a voltage. We know how many samples we should use. We know the LSB that we have to use, okay? And now we will study the counterpart of the analog to digital converter, the DSC. Why? Well, one important part of the analog to digital converter is voltage reference. Why? Probably you remember, for instance, the example, I don't know, of the flash ADC. It was the first one that we studied, and I told you it's also the fastest structure for an analog to digital converter, okay? And if you remember, it was based on a scale which I defined as a thermometer scale, okay? So what you do is to, for instance, start from here, you create 0, 1 volt, 2 volts. Let me erase. I will do it again. Sorry. I start from here, and I have 1 volt, 2 volts, 3 volts, 4 volts, and finally 5 volts, okay? So here I have different tabs. So I have different tabs here. I create a scale where I have different resistors. Oh, no, sorry. All the same resistors. So all these resistors have the same value. Well, actually, the first and the last one typically are half of this value because of the alpha LSB as I explained to you, but let's forget about it for a moment. And then what do? You compare your input voltage to each of these levels of voltage. So I compare my input voltage to 1. And I ask to this comparator if it's bigger or smaller than 1. Then I do the same for 2, 3, 4. So here I have several operational amplifiers which compare the input voltage to 1, to 2, to 3, to 4, and so on. So they tell you if your voltage is bigger or smaller. Then the output will be a series of 0, 0, 0, 0, 1, 1, 1, 1, and you know that your input voltage is between this value and this value, okay? Now, what happens if your reference voltage is not what you expect? In this case, we connected 5 volts, and by using this series of resistors, we know that the value here will be 1 volt, 2 volts, 3 volts, 4 volts, 5 volts. Of course, typically, there are way more resistors. So these resistors are just an example. If you have 8 bits, you have 256 resistors. So there is no flash ADC with only 5 resistors. It's just an example. But just to make an example, if VR is 5 volts, then I know that this value must be 1 volt. But what if VR, instead of 5 volts, will be 6 volts? Or 5.5? Let's make 5.5, okay? We believe here we have 5, but instead of 5, we have 5.5 volts. We have an input, we have a reference voltage which is 10% bigger than what we expected. Well, if this input voltage is 10% bigger than what we expected, here we will also have a voltage which is not 1 volt, but 10% bigger. So the voltage here will be 1.1 volt, not 1, okay? So the voltage that you find here is bigger than 1 volt. And what does it mean? Well, let's say that our voltage here is 1.05. We would expect to see this bit to be 1, which tells us that the input voltage is bigger than 1 volt. And that's true, because the input voltage is 1.05. But because here we have 1.1 volt and not 1, then the output of this comparator is 0, not 1. Right? So this bit is wrong, because the voltage appears smaller simply because the input voltage here is bigger than what we expected. If we have 5.5 volts here instead of 5, all these voltages appear 10% bigger, and therefore, in comparison, the input voltage appears smaller. This bit should be 1, but in fact we get it 0, okay? So you scale down all the values of the voltages that you measure. And you understand now that this is a crucial part of an analog to digital converter. It's a crucial part because all the data, all the information that you get here at the output is referred to the input. It's referred to the reference input voltage. If you change the reference input voltage, then also the output changes proportionally to that, which is terrible. If you have a great analog to digital converter, and then you have a terrible reference, then you get a terrible data at the output. You can try to make as perfect, as precise as possible these resistors to be all the same, to have always the same difference of voltage between one tap and the other. But then if you connect a wrong value, a not very well-known value of the input reference voltage, then all this precision is for nothing, okay? Fine. So it's very important here to have a voltage which is very well known and very stable. Because you might know the value at the beginning. You say, fine, it's not 5, cool, it's 5.5. But I know it's 5.5. So I know this will be 1.1, and I take it into account when I convert back the digital data. It's fine. But then what happens if this voltage in time becomes 5.6? And at that point, you think it's 5.5, but meanwhile it moved to 5.6. You see? So you need not only a voltage which is very well known, but a voltage which is also constant in time. And today we will study about these reference voltage sources. Another application of these reference voltage sources is the digital to analog converter, which is the opposite of the analog to digital, okay? We just flip these two letters. These devices convert digital code to analog voltage. We need them in many applications. One of them was, for example, the successive approximation analog to digital converter. You remember that at every step, we change the value of one bit from the MSB to the LSB, and we tried to approximate step by step the value of the input voltage. How we did it? We created, with the digital code converted so far, an analog voltage, and we compared to the input analog voltage. And then we decided if the next bit will be 1 or 0. Go back to the first lecture, I think it was lecture 1, to see how it worked. In that case, in that structure of analog to digital converter, we needed inside a DAC So a converter from digital code, the digital code we converted so far, to an analog voltage, which was necessary for the comparison with the input voltage, okay? So first of all, today we study these digital to analog converters. So in this case, from the digital code, we go back to the analog voltage. The structure is very simple, and guess what? It's again based on operational amplifier. And specifically, it's based on, well, I don't have it now on the board anymore, on a current to voltage converter. Instead of having a photodiode now, we have current sources of current. But the structure is the same. So here we have these sources of current, and they arrive at this node, they sum. We have different sources of current. They all sum here at this point, at the negative input of the operational amplifier. Then they flow through the resistance R, and they cause an output voltage V out. Okay? Please note the values that I use for these current sources. They are not random values. They are I, 2I, so twice the value of the first current, 4I, 4 times the current of the first generator, and finally 8 times I. Of course, you understood these correspond to digital codes, because they are powers of 2. Now, you see that there are some switches. So I can connect this current source going either to the resistor R causing an output voltage, or going to ground. They always produce the current. They don't care where it goes. It could go to R and cause an output, or they could go to ground. They don't mind. They always produce the same current, and you will see later why I'm specifying this thing, okay? So here it can go to ground, or it can go to the resistance. If it goes to ground, it doesn't give any contribution to the output. If it goes through the resistance R, then it gives a contribution to the output, okay? For instance, if we want to create a digital code 9, if we want to convert a code 9 into, if you want to convert this code into an analog voltage, then you switch on the generator corresponding to 8 times I, and the generator corresponding to I. In this case, we sum up the two resistances, and we get 9I. And of course, the other two generators of current are connected to ground. How do we achieve this kind of resistance, of this kind of values of current in powers of 2? I, 2I, 4I, 8I, and so on. We use the so-called R to R resistance ladder. So instead of the generators, now I connect this ladder, which is fed by a voltage input VR, okay? Please note that again, the current could go through the resistance, or as you see, it's connected here to ground, and the current goes to the ground. But in both cases, the bottom part of the resistance, the bottom terminal of the resistance, is always connected to the ground. When the switch is on the position 0, it's obvious. It's connected directly to ground via the switch. But even if you select the position 1 of the switch, it's still connected to the ground. Because if you notice, it will go, it's connected, the resistance, to the negative input of the operational amplifier. And you know that there is no voltage difference between the positive and negative input of the operational amplifier. Therefore, this point here is at the same potential of the ground, because the negative input is at the same potential of the positive input, which is at ground, okay? So, as you see, in both cases, this point is at the ground, either directly, because we connect it to the ground, or indirectly, because we connect it to the negative input of an operational amplifier, which is then at the same potential of ground. Therefore, what we can do, this is what I was explaining, in fact. What we can do is to replace here, instead of the switches, the ground. Because from the potential point of view, these points here, the bottom terminals of all these resistors, are connected to ground. So let's cancel all this circuit, and we replace it with a ground. Why we do so? Because now we can easily calculate which is the current flowing through each of these resistance to R, okay? And then, once we know the value of these currents, we know the current which flows here through the resistor, okay? Fine. How to calculate this circuit is very simple. We use basic electrotechnic calculation. So we have two resistances, 2R in parallel, and the parallel of two resistors with the same value is half of that. So the parallel of 2R and 2R is R. So instead of these two resistances, we can substitute R. But then what we have? R in series with another R. So we have 2R. Okay? R in series with R. So again, we have a parallel of 2R and 2R, which, guess what, is R. But then again, we find a series of R and R, which is 2R, right? And again, now we understood the trick, we find a parallel of 2R and 2R. At the end of the day, you find that the total resistance of this circuit is R. If you solve each step of this ladder, you find to a value, total value of the resistance, which is R, which is quite interesting because you can continue to have as many steps here as you want, okay? You can continue to have R to R, R to R, R to R, and still the total value of the resistance will be R, which is quite counterintuitive for someone. Fine, it was very funny, but then let's go back. Now, we go back to the first step. Here, we input a voltage reference VR. And this voltage reference is applied to a series of R and R. So this point will be VR divided by 2, because it's half of the input resistance, of the input voltage. We have two equal resistors, therefore here we have a voltage divider and we get half of the input voltage. But then we remember that this R was initially caused by the parallel of 2R and 2R. So let's go back and let's plug again 2R and 2R instead of R. We obtain these two resistances. And we remember that this 2R resistor was in fact caused by a series of R and R. So instead of this 2R resistor, we plug R and R. And again, we have a voltage divider. Here, we have VR divided by 2. And since we have a series of two equal resistors, again, we divide it by 2. So we get VR divided by 4. So the voltage here is VR divided by 4. And if you continue, you realize that at every step, you divide the voltage by 2. VR divided by 2, by 4, by 8. Because at every step, you have a voltage divider between two equal resistors R, and one of them then can be seen as a parallel of two resistors 2R and 2R, and so on, and you continue, okay? And now you realize what happens when you calculate the current. The first resistor has a value to R, and the voltage on that resistor is VR. So you have a current VR divided by 2R, and we call it I. The second vertical resistor has the same value, 2R, but the voltage is half of that. So the current will be half. Then the third vertical resistor still has the same value to R, but the voltage is 1/4 of the input voltage. Therefore, the current will be 1/4, and so on. At each step of this ladder, the voltage is divided by 2, and therefore, at each step, the current is reduced by a factor of 2. Therefore, you get I half, I4, I8. And of course, if you reverse it, if you can call this I, this will be 8 times bigger, okay? This will be 2 times bigger, and so on, okay? So here, you can connect back this ladder to the operational amplifier, and you can select different values of current in ratios of power of 2, okay? Another system to create, very cheap system, to create a digital to analog converter is to use a PWM. PWM stands for pulse width modulation, and it's something you can see probably in any modern microcontroller. If you ever played with some microcontroller in a rainy day, you definitely know that there is a PWM mod. Very often there are more than one PWM modules on any cheap, even very cheap microcontroller. What is a PWM? It's typically used to control motors or other systems where you need to create a variable voltage. And you basically create an output which is 0 or 1 with a proper duty cycle, okay? So you can create in time a pulse. The output voltage can have only 2 values, either 0 or VR, and you have the time when it's off, the time when it's on, and the duty cycle typically is defined as the time on divided by time on plus time off, okay? This is the duty, typically it's called the duty cycle. It's very easy to do it in electronics because you simply have a counter. You have a counter which counts the time, and it compares to some register. When, for instance, you have a register of 8 bits, you have 256 units. So there is a clock. You count, which is something very easy to do in electronics. And I don't know, when you arrive to 110, you turn an output on, and when you arrive to 256, you turn it off, okay? The microcontroller does all of this automatically, so you don't have to create any software. There is a module inside the microcontroller which automatically, without loading of computational power your program, and independently from your program, will perform this task of counting, increasing a register, comparing a register to 110 and 256, and then turn on and off the, or turn the output to VR or to 0. Why I emphasized independently from your program? Because if you do it in your, of course you can do it also in your program. Nothing prevents you to do it like programming a software which does this task. But of course, if your software does something else, then if you stop counting at some point because you have to do something else in your program, then you will have a delay in the execution of this task, and therefore the ratio is not respected anymore. Okay? So that's why in microcontrollers you have these modules which do this task for you by themselves. And then what you can do is to apply a low-pass filter to get the average value. If you have this duty cycle, you will have a large average value. On the contrary, if you have this duty cycle, you have a lower average value. So what you do simply is to change the duty cycle, the time the output will be on, and with respect of the time it will be off, and then you get a different average value. Of course, you must be careful because you have to filter out very well this very fast change of voltage, otherwise you will have the high frequency component given by this rapid change of voltage. And of course, you must know that the output voltage, the output created by the DAC, so this output, the average output, can change at a frequency which is, of course, much lower than the frequency of the PWM, okay? So you cannot expect to have an output voltage which changes at the same speed of this. Fine. If this takes 1 millisecond at each cycle, you cannot think to update the output of the DAC with the same speed. You have to give some time to average down, okay? So it can be applied for lower frequencies unless you have very high speed PWM, but that's not typically the case, okay? As you see here, we need a voltage reference, both for the ADC and for the DAC. We need a voltage reference. In this case, it was for creating currents which then are transformed into an output voltage proportional to the digital code. Also, in this case, it's very important to have a very good reference, because if you change the voltage reference here at the input, then all these currents will have a different values, and when we inject them in this operation circuit with the operation amplifier, then we get an output voltage which is different. So now we will study very briefly voltage references. As I've shown you, we use them for both ADC and DAC, okay? There are two basic structures for voltage references. One is the shunt, and which is typically given in 2 terminals, and it doesn't work by itself. We need to add a resistor to the shunt to make it working properly. And then there is a series which has 3 terminals. The shunt, the principle of the shunt is very simple. You take your shunt, you connect a resistance R1 in series, and then you have a voltage source Vs. Vs can change. The output current from here to the load will change, but the shunt will keep the voltage output Vr at the same value, 5 volts, 2.5, whatever. Let's say that this shunt is designed to produce 5 volts. Fine. You can absorb from here a different values of current, and it will keep the voltage there, 5 volts, okay? We can model this shunt as a source of current, Iref. How does it work? Let's say that you connect a load to your voltage reference, and this load has a resistance R load. For instance, this series of resistances, okay? And this load absorbs a current I load. Then the resistance R1 will see a current which is the sum of I load plus the current Iref, which is the current absorbed by the shunt, the reference current absorbed by the shunt. The output voltage Vr will be the difference between the source voltage and the resistance drop, the voltage drop on the resistance here. So the output Vr will be Vs minus the voltage drop on the resistance R1. And the voltage drop on the resistance R1 simply is given by R1 times the current R1. But we know the current R1 is the sum of the current in the load and the current in the reference. So finally, we can write that the output voltage, VR, the reference voltage that we produce, will be Vs minus the resistance R1 times the sum of these two currents, Vref plus Iload. Do you want VR to be constant? Yes, of course, we do want VR to be constant. So, if Iload changes, for instance, let's say that Iload increases, then Iref automatically decreases. So that the sum, Iref plus Iload, will be always the same. Iload decreases, no problem. Iref will increase, so that the sum of them will be constant, and the voltage drop on R1 will be constant, and therefore VR will be constant. So we can say that if Iload increases, then the reference current decreases to compensate it and have a total sum Iref plus Iload constant. While on the other hand, if the Iload decreases, Iref must increase to compensate this decrease of Iload and still have the same total current in the resistance R1. Okay? What's the problem? The problem is that the reference current cannot decrease indefinitely. There is a minimum value of reference current that I called Iref min. Okay? Once you arrive there, if you increase the load, the reference current cannot go down anymore, and therefore the value of the current in the resistance R1 is not the same anymore. Okay? And therefore you are not regulating this voltage to be 5 volts as you want it anymore. So we must avoid this condition. We must take our project and check what is the maximum value of the current which will be absorbed by the load. This value. This will be the maximum load current. And then we must check which is the minimum reference current in the shunt. And this will be Iref minimum. Then we know that at this limit condition, when we have the maximum load and the minimum reference current, the resistance R1 will be Vs, which is the voltage source here. So the resistance will be Vs minus Vr, which is the voltage drop on the resistance R1, divided by the sum of these two currents, which is the current which flows through the resistance. Okay? This is the limit condition, but of course, the system works if you have this resistance R1. In that case, the condition is met and we can still have our 5 volts of output. But it works also if you have a reference current bigger than the minimum. Iref minimum is really the minimum it can absorb. But it can produce also a larger reference minimum. Still fine, okay? So the resistance can be this value, Vs divided by Vs minus Vr divided by the reference, the minimum reference current, or the plus the maximum load current, or you can have also a larger reference current. You can have the minimum, which is really the minimum you can get, or simply a little bit bigger reference current. Still works, still can produce this reference current if it's bigger than the minimum. If you have a bigger reference current, it means that the resistance must be lower, okay? So the resistance can be, generally speaking, lower or equal to Vs minus Vr, the reference, the minimum reference current plus the maximum load current. This is not the only problem. You have the opposite problem. The current in the shunt cannot increase indefinitely. There is a maximum value of the reference current. So, in this case, you have the opposite condition, limit condition. You have the minimum load, so when you reduce the load, you must increase the reference current to compensate the lower current absorbed by the load, but this current cannot increase to infinity, okay? So in your project, you see the process, okay, this is the minimum current I'm planning to absorb. I plug it in the equation together with the maximum reference, the maximum reference current the shunt can absorb, and you calculate the limit R1. But of course, it can produce a current which is less than the maximum reference. It doesn't complain if instead of asking the maximum reference current, you ask a current which is slightly lower. Therefore, the current can be larger or equal of this value. If you plug together these two conditions, you arrive to a system where the resistance must be between these two values, okay? You calculate the two limits, and then you pick up a resistor which is within these limits. This means that when you select a shunt, you cannot just pick a random resistor from your resistor box and connect it there, okay? If you're lucky, it will work and you won't have any problem. But if you want to make a good design, you have to calculate the limits your shunt will work on. And then you have to calculate a resistor, which you have to select a resistor which is within these limits, okay? The other voltage reference is the series voltage reference. In this case, we have three terminals. We have the input, the ground, and the output. You can model this reference as a variable resistor and a generator of current. So, in this case, I have a current which goes to the load, I load, which changes. It might change and have different values. Then I have a variable resistor which will change in order to have a variable voltage drop so that the difference between the input and the output voltage will be always the same. Let's say that we have 10 volts at the input and you want a 5 volts output, okay? You change the load, but the difference between the input and the output must be always the same because you want the output to have always 5 volts. So if you have 10 volts at the input and you have 5 volts and you want 5 volts at the output, you must always have 5 volts of difference between the input and the output. So if the current absorbed by the load changes, you must change accordingly the value of the resistance RV in such a way that the voltage drop between Vs and Vr is always the same. And Vr, therefore, will be always constant. Why do we need IQ there? IQ is a quiescent current, and that's a little current you need to generate a voltage drop on RV if there is no load applied. Let's say that you applied a zero load, or generally speaking, a load so big that the current is basically at zero, and you need a little current to generate that voltage drop there on the resistance. Otherwise, you cannot generate any voltage drop if there is no current in the resistor, okay? Be careful. It's not a transformer. So you don't transform the voltage powerless, without wasting any power. There is power lost here. Here you have a current load which goes on this variable resistor, and it has a power lost on that resistor. So this is probably not so important if you are considering these circuits where the reference doesn't absorb a lot of current. But it might be a problem, because then you have the resistance RV times the current squared, and this is all power which is dissipated by the voltage resistance, which generates heat, and in some circuits it might be an issue, okay? So be careful. First of all, you waste energy, which is, that's it, it's how it works. But then don't forget that energy, well, maybe it's important if you are creating circuits which consume very, very little energy, and you really, every single microwatt in your circuit is important, okay? But generally speaking, don't forget that it might generate heat, and this heat, if it's not dissipated, we might have some effect on your circuit. It might generate some heat which is maybe affecting some other device in your circuit, okay? So be careful. Another problem is the dropout voltage. There must be a minimum value of voltage between the input and the output, okay? So the input voltage must be sufficiently larger than the output. Vs must be sufficiently bigger than the output, because you cannot have zero difference between Vs and Vr. There is a minimum voltage. You take your data sheet, and it's written there that if you plan to have 5 volts here, and the input, you must have then Vr, 5 volts, plus the dropout voltage. Otherwise, the system is not able to regulate the output, okay? Fine. Now, how to select voltage references? If you go to any website of companies producing voltage reference, there are a lot, really, hundreds of these voltage references. So now I will try to give you a very, very basic introductions to the most important parameters of these voltage references. Those parameters you must watch to select properly a voltage reference for your circuit. The first important value is the initial accuracy. It can go from 1% to down to 0.02%, something like that. What does it mean? It means that you buy a voltage reference of 5 volts, and you have an initial accuracy of 0.5%. So the actual voltage that you find out of your reference will be anywhere between 4.975 to 5.025. Be careful, because if the company is honest enough, typically they also give you some statistical distribution. So they tell you, okay, this is the initial accuracy we expect typically to be within 0.5%, but we tested, I don't know, 1,000 of our products, and I tell you that, I don't know, 20% of the products is within 0.1%, 25% within plus minus, I don't know, 0.2%, and so on. So they have a statistical distribution. So you know that maybe the value might be distributed according to, if you produce a lot of products, of course. If you only need one, you test it and you calibrate it, and Bob's your uncle. If you produce, if you make mass production, then you know that the mass production of your circuit will be influenced by the statistical distribution of the voltage reference that you buy, okay? As I told you, we need this voltage to be constant. Why? Because, for instance, if you use this reference to feed an analog to digital converter, which is, for instance, inside the multimeter, then if you have a voltage which is not 5 volts as a reference, but is 5.025, well, it's not a big deal. You can calibrate it. In your software, inside your multimeter, we say, okay, fine. The input, I measure the reference voltage. I know that it's not 5, but it's 5.025. And therefore, I scale down all the measurement that I make because I know that at the input here, I don't have 5, but 5.025. I make the calibration, and since the output, the reference voltage is bigger, I recalculate all the digital data that I obtain, knowing that what I measure corresponds to the digital data referred to 5.025 and not to 5 volts. Okay? And that's not a big deal. It's enough to connect a source of voltage very well known to the input. You know that you connect 1 volt, okay? But you read something else on the screen. Well, you scale down all the measurement, knowing that the reference is bigger or smaller than what it was supposed to be, okay? But this trick works only if the reference is different than what you expect and doesn't change in time. If your reference changes in time, for instance, it's 5.25 today, but it will be 0.024 in 1 month, then you should make a new calibration. And so on. This is the reason why when you take the manual of a good multimeter, they tell you that the accuracy of the measurement is within a certain range, within 24 hours from the calibration, in a bigger range within 3 months, or even in a bigger range within, if you use your multimeter, within 1 year from the calibration. Why? Because simply the reference drops or changes, generally speaking, in time. And therefore, if you make the calibration today, all the values that you recalculated are okay if the value of the reference doesn't change. But since we know that it changes in time, we know that the longer we wait from the calibration, the more VR, the reference voltage inside the multimeter, will change from the value we calibrated, okay? And therefore, the manual of the multimeter will tell you that your accuracy must be larger because you have a worse knowledge of the reference inside the multimeter, okay? So, a very important value, characteristic value of the voltage reference is the long-term stability, which is given in ppm, which stands for parts per million, for 1,000 hours, okay? It tells you how much it changes in 1,000 hours. Another very important value is the temperature coefficient. Maybe you have 5 volts at 20 degrees. But if you change the temperature, then also the output voltage will change. And therefore, you must consider that if you are going to use your system, not in a room, in a laboratory where you have 20 degrees, but you're using it, I don't know, at the North Pole, but even without going to the North Pole. If you're using it outside in Prague in a night of February, easily you can go down to negative 15 degrees of Celsius. If you're using it in summer, you can go up to 40 degrees. So you have 55 degrees of difference of temperature. The voltage reference might change and not be the same, or generally speaking is not the same, for this large change of temperature. Be careful in this case, because if you watch at the tables, they typically give parts per million, the change of the temperature coefficient is given, the change of the voltage reference expressed by the temperature coefficient is given in parts per million over Celsius, over degrees. But very often this is not linear. So you cannot say I change the temperature by 50 degrees, and therefore I multiply times the ppm per Celsius, and I get how much ppm changes the output in that range. It's really not like that. Very often you must go to the datasheet of the voltage reference, and if the company is honest enough, like in this case, they will show how it changes in temperature. And for instance, if you are using the voltage reference in a range between -50 and 0 degrees, here you have almost, let's say, 4 millivolts of change of voltage, which is quite a large difference in this range. But if you use it in this range between 0 and 50, again you have a difference, a range of 50 degrees between the maximum and minimum temperature you are using your device at. But as you see, the change is only about 1 millivolt, because here in this part of the characteristic between 0 and 50, the voltage is more stable. Okay, so be careful. Not take just the temperature coefficient and multiply times the difference of temperature. Always check if in the datasheet you have the analog plot of the output voltage versus the temperature. Then there is the noise, which is not accuracy. That's a different thing. You can have wait, this is okay. Yes, in this slide I show the accuracy. Okay, so if you want 5 volts reference, you might have this voltage here, which is rather close to 5 volts. So you have a good accuracy, it's 5.05. Or, for instance, you have a bad accuracy here. Of course, I'm emphasizing, I don't expect any real voltage reference to produce 4.6 volts if you want to produce 5 volts. But this was just to emphasize. Instead of having 5 volts, you get 4.6, which is a bad accuracy. But the noise is almost the same. In this case, we have the same accuracy. The average of the two output voltages is always 5.2. We have the same accuracy. But around this 5.2 volts, one of the two voltage references swings more, okay? So it has a larger noise. What does it mean? It means that if you use this voltage reference to power your analog to digital converter, your output data will be affected by this noise. For instance, we have a flash ADC here. It means that we are converting very, the conversion rate is very high. So if you convert the same voltage, let's say that we convert 4 volts, and the reference in some point is here, you get a larger voltage because the reference is lower. On the other hand, if I still convert the same voltage, 4 volts for instance, but just a few like milliseconds later, for instance here, when the reference is bigger, then the same voltage, 4 volts, will appear smaller because it will be compared to a bigger input reference. So if your reference is smaller, your input voltage appears bigger and vice versa. Which means that at the input you will have always 4 volts, but you have an output voltage an output code, which will swing the very same way the voltage reference swings. So all the noise that you have here at the voltage reference, you will have it here at the output data, okay? That's why you want a low noise, because all the noise that you have at the input reference, you will have it at the output data, okay? And that's all for voltage references. Next lecture, we will talk about spectrum analyzer. Thank you very much for your attention. And as always, stay safe.